A very quick introduction to Squonk, which is a platform currently under private alpha development by Tim Dudgeon of Informatics Matters. Tim strongly believes that the reason computational tools are not being utilised effectively in research and development isn't because of a lack of functionality, but rather a lack of usability. Squonk's an example of a computational notebook. The computational notebook integrates the best commercial and open source computational tools into a simple-to-use, browser-based environment, and by doing so, lets you build up a full electronic record of your work. You can share this with others and replay with different inputs and/or different parameters. At XChem, we're joining forces with Tim and Squonk, and are hoping to develop tools within Squonk to make the process of follow-up chemistry after hits at IO41 more intuitive. In the not-so-distant future, your comp chemists will be able to write scripts into Squonk so that your biologists and synthetic chemists can use them with ease in their own customizable workflow, making collaboration on projects much easier. So we're just going to go through a quick example using Squonk. So this is the Squonk canvas, which is where your workflow works from. And we can open up a notebook. So we're going to look at some follow-up chemistry of a hit or some hits pulled from XChem Explorer. So we'll just load that up. And this opens up a set of cells, which are also down here. And they are essentially scripts held in a box, and you select your inputs, you get an output and pass it on to another cell. So we'll just hide those notebooks and cells. So here we have the output of XChem Explorer. And in this workflow, we're going to concentrate on using the smiles of those hits to think of some follow-up chemistry to start looking at bigger molecules that might explore the binding site a little better. So the first thing we're going to do is convert those smile strings into molecules. This is an RDKit script. And there you go, we've got some nice pictures of some molecules from those smile strings. So next, we run a poise reaction filter on the structures from here, and we pull out the molecules that can have some chemistry done on them. And in this workflow, we're going to concentrate on this molecule, which is paracetamol. So if we look for the amides from the paracetamol here, we can see which parts of the molecule you can break up to do some amide coupling with this amine here and this acyl chloride group. So next, we're going to apply a rule of 3 filter. The rule of 3 filter is specific to fragments, and we're going to focus on a molecular weight of at least 100 so that we know that we've got a fragment we can do some good chemistry on. So there you go, we've got the fragment with the amine group on it. Okay, so from here, we want to look specifically at those amide coupling reactions. And for this, we need an input library of acyl chlorides. So you just make this and input it as an SDF file. Nice big set, acyl chlorides. And we feed that and the output from the rule of 3 filter into a reaction maker with the amide coupling reactions. And we get a nice big set of potential follow-up compounds. Okay, so to narrow that down a little bit, we're going to look at constraining them by Lipinski rules. So we're looking at more drug-like compounds now, which we want to fall in with Lipinski's rules rather than the rule of 3. And if we have a look at them, we've got another big set of compounds, but they've been filtered down. Okay, so after our Lipinski's rules, we're going to try and pick a diverse subset of that set and narrow it down a little bit more. And here you can use different descriptors to pick your diversity set. You can use different metrics to measure how diverse they are, and you can optimize based on different things. Here we're going to optimize for diversity based upon exact molecular weight. So now we've got 10 compounds that we can investigate a little bit further. Okay, so at this point, we're going to take the geometry of the original hit, which is here, and we're going to feed that and the conformers, the structures selected as diverse, into a constrained conformers module. and that just generates some conformers for the molecules we showed earlier. And from here, we're going to do some docking scoring. So if we have a look at the original protein structure, so the apo structure, which we can load in. If I just remove this, this is left over from earlier. So we've got the apo structure of the protein, and the binding site is here. So we feed both the apo structure of the protein and the conformers that we've generated into a scoring function for docking, and then we get some results, and these are the scores here. So from there, we've fed it into here, so we can see which structures have got the best docking scores. So if I select the two best at the bottom here and click Run, we can go over to this, which is a NGL viewer for molecular stuff. And we can zoom in, and we can have a look at where our different hits differ in structure, and we can see where they're exploring the binding site as well.